So, welcome to my presentation, another kind of actor framework, the task X4. So, who am I? My name is Karsten from Viking Software from Hamburg, Germany. I'm working with LabVIEW now for 20 or more years. I'm CLA for 10 years, and my partner, Falk, and I, we have a small company in Hamburg, Germany. We do LabVIEW stuff. So, but now, let's first talk about the theory of ectomorphs. Okay, now I sit down. I hope you can hear me. If there are any questions, please ask. Interrupt me, ask, so I can answer everything. So, if you read Wikipedia, what the actor model is, you get some sentences I want first to analyze. So, the actor model in computer science is a mathematical model of concurrent computation that treats actors as the universal primitives of concurrent digital computation. Interesting sentence. So, what does that mean? So, first, the fundamental concept is everything is an actor. An actor is a data processing thing. You put information inside and get answers out of it. So, it's an entity to solve tasks or do a job, anything. Actor is an encapsulation from data, behaviors, and threads. So, a data processing entity. Next sentence. In response to a message that it receives, an actor can make local decisions, create more actors, send more messages, and determine how to respond to the next message received. Okay? So, what does that mean?
Change the state.
Yep, that's it. It can make local decisions and change its behavior. So, an actor is a kind of state machine.
It can be driven by a state machine, but not necessarily.
Yep, it can be driven like a state machine, but that's for later. So, actors need a mechanism to move messages from one actor to another. So you need message communication in an actor. So it receives messages and it sends messages. And an actor can create new actors. So you break down a problem and build several small actors to solve the whole problem. Okay. Next sentence. Actors may modify their own private state, but can only affect each other through messages, avoiding the need of any logs. So, if you work with an actor, you early or later have a kind of network. A network of small actors that communicate with messages. The messages are actors can receive the message somewhere, sometimes. There is no the actors could process parallel. So a message goes to an actor and then the actor does something. If the message goes at the same time to two different actors, you do not know when each actor works with the message and when the message is processed. It's parallel. So an actor must react to unexpected messages. So if an actor receives a message that it can't handle, so he needs to work to deal with that to avoid logs in the program. So, there is no assumed sequence to the action of an actor. So the actor can handle it when it wants. the communication between the actors is asynchronous. So each actor works at its own time. So actors are highly decoupled and controlled by exchanging messages. That's everything. So, summary of the key abilities. Actors are created and destroyed dynamically. So, a process spawns an actor or destroys an actor, spawns a new one, or spawns several actors from one kind to solve several processes.
Actors themselves do that.
Actors themselves do that, yes.
Not some abstract process.
No, the actor itself
can create
new child actors or create or destroy its own child. So, it's a network of independent and asynchronous tasks. Communication via messages, and each actor is, how we heard, is an event-driven state machine. So, the benefit is they are modular, scalable, reusable, and extendable, and have loose coupling. So if you have a good architecture, if you change the data of one actor, you don't have problems with other actors, no side effects. So, and because of the extreme parallelism, it uses LabVIEW's natural parallel execution system. Actors benefit from object orientation and inheritance. So if you work with OOP, you can make, yes, easier actors or improve them.
You cannot inherit everything though. You cannot inherit behavior.
Yep.
Using at least LabVIEW.
Yep, you can inherit everything. So, but I don't want to talk about actor framework. I want to talk about the actor model first. So, this is an example for a typical or for an actor thing we use. So, you have a LabVIEW application and you have a general SQL handler task. So, the LabVIEW application only talks to the SQL handler. And only the SQL handler knows the database driver, and so the database driver can work for several databases. You can work with MySQL, SQL, SQLite, Oracle, and so on. So you have a hardware abstraction layer on database level. So that's really easy to change systems. That's one example. Other example, a little bit more complex. We have a native CanOpen stack built with LabVIEW. So we have the LabVIEW application. The LabVIEW application has a CanOpen manager. The CanOpen manager handles the CanOpen stack. So it spawns the CanOpen service tasks, and these tasks have the hardware abstraction layer to the CAN. So you can use at this level different CAN mechanisms. So by changing the CAN device, you can use with NIXnet, you can use it with vector cards, you can use it with every other card that you can talk with, that you can build a driver in LabVIEW for. And yes, we have built, let me call it simulated CAN over Ethernet. So for testing by Vikings in-house, we don't need CAN cards. We have built our own CAN over Ethernet stack. So that works because I can only change the behavior at this level. So simulating or other things. Next part, the CanOpen manager spawns tasks for all the CanOpen nodes, and all the CanOpen nodes talk to the CanOpen database. So it's a real complex building with messages flying all around and states everywhere. It's really
so according, including messages peer-to-peer, not necessarily to the creator.
yeah, peer-to-peer, not to the creator. Everybody can talk to everybody if he needs to. Yeah.
Yeah, because they all have address.
All have addresses, all can get the addresses of the other actors, and that's really nice to work with.
They can subscribe, publish, go through the addresses,
Yep.
send in the corresponding messages.
Everybody can. I repeat it via a micro. So everybody, every task can subscribe to other tasks. So that's the theory. Now let me talk about what is task X for. So our task 4 is a tool set or a framework we use at Vikings. It's the 4th generation, so it's task 4. And we started building it at 2004. It's an actor model, but not an actor framework. So we don't use actor framework. Why? I tell it later. Our tasks, or better, our actors are called tasks because we don't want to use the same name, because people with lower experience in LabVIEW have problems with the name actor. They get frightened about it.
It's just because of the implementation and NI pushes.
Yes.
Which a lot of, it doesn't mean that actor framework is a bad thing. It's
Yes.
just what NI calls actor framework. Its particular implementation has, well, quite severe deficiencies pointed out by many people when it came out. Well, when it well.
Yep. Actor Framework is a great piece of software architecture, and it works for several uses, but we don't use it, and the reasons I tell in the next minutes. So, I don't want to discuss about frameworks. Every framework has its benefits, so our framework is one under all the others. I only want to share a solution or concept we work with, and we work with success since several years. So, what are the challenges in our daily business? We have to handle customer requirements. So, these requirements are often similar, but almost different. But it would be great to reuse code. So, if you have built a data acquisition for a special card only this customer uses, or you get the card from another customer with special use cases. So you can change, yes, you can reuse the code. That's a thing we want. So, next point. We want to react fast and easy on change requests. I think this is a thing everybody who works with customers has experience with. Customers change their ideas daily. So, and sometimes we want to involve customers in the development. But the most customers are not CLAs or don't know big architectures in LabVIEW. They are on CLD level. So, another part we work with is refactoring and prototyping test systems. Again, the people that work with the systems are only CLDs and not big software architects. We need simulation and hardware abstraction. Sometimes we want to change the devices because Vikings doesn't have the device a customer has. Okay, several things are be able to simulate with the Macs, but some other devices or behaviors are special. So, we have some general software requirements. We want sustainable software development. We want to work with modules with low coupling and reuse the modules later in other projects if they are worth it. We want to develop APIs for later reuse. So we don't want to build only one needed function. We want to build the whole system for reuse. And we want to benefit from LabVIEW's low-level functions. So we work with object orientation. We work with LVOP, with LabVIEW object orientation. We work with goop. We want to benefit from inheritance and polymorphism from object orientation. We want to use data by reference if we want that or we need that. We want to work with event-driven asynchronous tasks. So for us as CLAs, it's really easy and simple to do. But the customer is almost a CLD. So easy and simple depends on the skill. So the customers often have different education requirements and needs. So if I talk about object orientation, several customers are getting frightened and getting such big eyes because object orientation is, yes, really a secret for them. But everybody who works in LabVIEW with clusters has worked with object orientation in LabVIEW. It's similar. So several of our customers are not as familiar with LabVIEW as we are, or they overestimate their own skills. Everybody knows that a customer comes to you, tells you something about a program or a solution he needs, and yeah, I can maintain the software afterwards by my own. No, he can't, because he don't understand as much from LabVIEW as we do. Or sometimes they underestimate the complexity of a project. But okay, almost the customers don't want to understand the big architecture. They only want to edit some VIs, and mostly these are the user interfaces. They want to change the color of a button, they want to add a new function, but they don't want to change the whole architecture from the top of the UI down to the drivers. So our attempt is to merge all the needs from CLAs and CLDs and get a more powerful tool. And that tool in our uses is this task 4 ectomorph. So, any questions to this point?
We want to see the implementation.
Yeah, hopefully I can show the demonstration. The laptop is a little bit crude these days. It makes a lot of blue screens. So first the theory. The first part, what you need is a task manager. So the instances are handled by an API. The task management is group-based. So the API handles the tasks from outside. So it's a remote control for VIs. For VI server VIs. The API can invoke new tasks or destroy tasks. In other words, it's a dynamic VI handler for VI server. Create, destroy things.
So this assumes some external code that will be creating and destroying these tasks.
Yeah, it's an API. It's an API to work with every type of VI. You can start primitives. Primitive VIs that only produce a heartbeat or something like that, or bigger structures. It's only the first part is only a VI server handler. Start, destroy, work with. So, okay, it's not so easy. It's object oriented. So, on the first level, we have only primitive VIs with no inputs and outputs. So we create this VI. It started and works up to its own end, or if you kill it. The second level is a task with a variant as input. only to give data to the VI. It's the same, no big architecture inside, it's only created and it works to its own end, or it can be destroyed from the API. So then we have some specials. So don't look at the green one, it's not what I want now. The blue one, the typical panel, a user panel. It's a panel that comes in front to interact with the user. Too small. So this is the first one that interacts with the architecture inside. So it's a message-based system, and here we have the first interaction of messages. But it looks almost the same. So you have a class that creates a panel class task and can interact with this class or with this task via messages. The first two are only, there's no interaction inside. You can only start and stop them with via server. So create, start, stop, halt, destroy. The second one, the red one, is for subpanels. Subpanels and panels are almost the same, but if you want to want to build complex user interfaces, you can use them as subpanels. So you have a panel that is presented in the subpanel container from LabVIEW. Everybody knows that feature? So the most important things are you can start a task, use it for black box things in the background, or you can use it as a panel to interact with the user. Or use the same one as a subpanel. So the green one is a special. The green one is a method that you can use as a sub-actor of a panel or something like that. And this one opens a TCP/IP tunnel to a corresponding machine. So if there is a port open on the corresponding machine, the two can get together and can interact via TCP/IP. They can exchange messages via network. So the messages can work in the local instance of your LabVIEW program, or can work through TCP/IP over the Ethernet or things like that. Real-time, for example. So, that's everything I need. The communication is implemented with the API. So, you have the VI send message to task. So you send a message, and you can send data with the message to the task from the variant type. So you can send everything. You can send classes, you can send complex structures, or you can only send an order or a request. We have decided that we want to use user events for communication. So we don't have a queue-driven message handler, we have an event-driven message handler.
Why? Why did you prefer event structures to just regular use?
It is an old decision. So it was a lot of years before when we decided that. So we thought about using the events because it should be the future. We didn't expect that the implementation of the event-driven, the event system is so slow.
That's my point. The event structure has a queue behind it.
Yeah, sure.
But it's much slower in my experience than a regular queue. So why bother with the event structure, which requires additional nodes to set it up and then to clean it?
It was a decision. It's a design decision. It was. I can't explain it these days. It was a decision. We do you have an answer, Falk?
This time, LabVIEW 2012, 2013, the performance of queue-driven and message-driven state machines was
Similar?
similar,
Yep.
very similar.
But the event structure it require. I mean, no question you should use it for
Okay.
interacting with the user, right? But for just a message receiver for a custom event, that is much more what's the correct English word? Sorry, you guys are German, I'm Russian. So laborious to set up. More
Yes,
difficult.
but this is a point where our API comes back.
And it is slower, as we know.
I don't know these days. I have to benchmark that now.
Okay.
But this implementation of the events is made by the classes. So you only have the class, the template, and it makes everything for you. So you have only to react on
Okay.
the message you get.
So you encapsulate it.
It's encapsulated, and you don't have to concern about the event handling. So it depends on the task with which messages it can handle. So if you have a task that is for user interaction, so it has different messages than a data acquisition task. But they have several messages in common. Show or hide the front panel. But for example, start the task, stop the task, configure the task, destroy the task, abort the task, exchanging messages, send a message and get an answer immediately back. Things like that are all implemented with the API. So
You support synchronous message with the acknowledgement too?
mm-hmm. Yeah, we support synchronous messages.
So why didn't you abstract it too, so that the user could use say AMC library, right? Synchronous message library, or just simple queues, right? So you could make a class that is like, okay, send a message, but how I implement it and what I actually use underneath. I could do whatever as long as it sends the message. And okay, we agree that the data goes as a variant, not as a string with a message, right? So this is still a data-based message, and this is not like Active Framework uses the separate class for each message, which is a lot of coupling. Additional measures need to be taken. Additional classes created just to decouple. That's ridiculous. So why didn't you abstract the communication?
It wasn't necessary yet.
Okay.
That's the only answer I can give you. For our uses and concerns, it was always okay. So you can encapsulate it or work with a class inside, but then you have the problems. The other, for example, the active framework has two. Everything is an actor, but everything is a class. So.
No, but apparently you don't you don't make messages to classes, right? You don't make them to be classes, so that you don't have to worry about it, because they are not messaging. Messages are not classes. The receiver has nothing to do with the sender has nothing to do, no business in knowing what the receiver will do with the message.
Yep.
That's the core of the benefit, the basics of the decoupling. And when you actually make a message that you have to pass to the sender with the way it will be processed, that's preposterous.
And that's the point where we have this message combination with message string and
a
variant.
Yes, or
so you can
string.
put everything in the variant, and if the receiving task can't handle that,
It's a business. Whether it will ignore it, whether it will send back another message, it's the business of the receiver. The sender has nothing to do with it.
Yep.
So, but there is a second question. There was alternative you chose. Why did you choose for the data itself that comes with the message? Why did you choose variant over, say, string? which we can flatten everything into string, and then that's if you already serialized, you can send it over the network like that. If you have a variant, that's still kind of value that sits. You have to serialize it before sending it over. It's a reason, right? Because it can accept all these strings.
The variant has one benefit. It makes the data corruption not so easy. So you always have a concept or a container where the data is inside, and the container guarantees that the data inside is correct. So if you put a not working variant and try to cast it to something else, you get an error.
From the programmer, point of view, from the level we have exposed to us, flattened to string and unflattened from string is at the same level of abstraction as using a variant and convert from variant to whatever class they want to cast to.
But this is again a decision we made because we want to make it easy for users. So a string serializing and deserializing is something you can understand if you know what you're doing. But if you have a customer that's not as experienced, he gets problems with that.
Okay, right. So at least with variant, you don't have to do serialization. You just wire the variant in, and that's it.
Yep.
You still have to.
And you can have the benefit that you can put additional attributes to the variant.
Right.
So,
Yes.
so you can build things that you need in the actor framework or in the actor model. So you can put in the back-sending address or something like that as an attribute.
Well, that can go as a part of the data.
Sure, it can. Everything is possible. But with a variant, it's compatible. So you don't need all the complexity of the data type. You need only to know that you have a message and the variant. And if there are attributes hanging on the variant, okay, if you don't know what to do with that,
it's more flexible.
it's more flexible.
structure.
Yeah.
Okay.
You can do more things with that.
It's fine. I did it the same way. I used variant, not string. But the AMC say uses strings. That's why I was asking why.
AMC is doing it like that, yes. But let's say we started developing it on 2004. So a lot of things went parallel. And when I saw the AMC, I have made my decisions several years before.
Yes.
So I didn't thought about that anymore. It was good and it works. So, task types. Tasks are independent actors that we have found out earlier. The design pattern is an event-driven state machine. The tasks are classified. So, the main data class is LabVIEW OOP based. So, templates for several needed use cases, yes, exist. So, that's a typical look of a task, task 4 task. So you have at the left is the initialization. Hard word. So the next part is the registering of the events. And then you start the front panel or unlock the front panel and give occurrence back to the caller that the task is started. And from that part, the task only runs in the while loop. And the while loop is a normal event-driven state machine. I can show it in the demo if my laptop is with us. Since the last update, it makes blue screens. So, and to make it more easier, we have here this VI. This is a simple VI that only handles standard messages. So it knows what to do when the message came, order show front panel or order hide front panel. So you need not to implementate these primitive events or primitive tasks in the state machine. It's always done to place this thing here. So, the data class implements the message system to the task. So, by this one here and this one here, everything is done with the event-driven state machine. You only have to use the states or register the events that you want to use. So here you see the typical message that comes in from generic, from the main income, and from its own child tasks. So here I handled all the messages from this task, this actor. The message is here, the data is here. So, but if you want, or if you know what to do with the data, you can do more. If you only want to get the message, so you can do that. There's no deadlock situation. The data class implements standard messages. Yes, that's this one here. So for more special types, for data acquisition, actors, for example, I have a more complex standard VI for standard messages because it needs more to do. And the class implements the task management. So again, by using this system class, you have implemented into the system class the system to start new tasks. And there is the big loop. So this class implements the way to start new tasks and destroy your own childs. So, what's our summary? On the one hand, we split the task into independent actors. So we have actors for looking at the time and send every 5 minutes an event to do things. Or we have a background task that handles things on the data system, that looks if the data management is okay, if the space on disk is enough, and things like that. And if the space is not enough, it sends a message to the main task, please tell your user to clean up space on disk. So everything there on the left side is for the architecture. So it's LVOOP or group-based with asynchronous event-driven state machines, and with the back channel we have synchronous messaging. It's possible. On the right hand, we have well-known concepts for CLDs. The normal event-driven state machine is one of the basic templates from LabVIEW. So, and it's easy to understand and to modify for not as experienced users as we are. So, the big problem in actors, I think you know that, is everywhere are flying messages all around. There are a lot of tasks, a lot of VIs doing things, sending messages through the whole system, and you have to tame the beast. You don't know what is happening if you send one message. So an event, a cascade of events starts in your system and things are happening and you don't know why, sometimes. So we have some tools for that to analyze. So first of all, one of the biggest points you need is, or you need to understand is, we have almost the same look and feel in all tasks. So if you see one task, you know how one task is working. You can easily understand the next one. So I told this is a concept I started in 2004. So when I have an old project these days, and I open the old concept from 2000, let's say 2010, I can read the VIs and I can understand them. They are not as well designed like these days, but in the fundamental concept is the same. You have a task, you have the same look and feel. It works in the same flow. That's one of the big points. So we're working with packages that At the time, we use VI Package Manager. We use the JKI. Is it VI Package Manager? It's VI Package Manager, yes. And we will use the NI Package Manager in the future. So we have design patterns that are similar. Examples, templates. So there's a common style guide and a common look and feel. And all this works together, so you have a system that's easy to understand for not as experienced users. So next part we have a task manager. The task manager is a program that works via UDP with our programs. So we can look in the program's task list and can analyze what tasks are started at the moment. And we can inject messages from outside for debugging. So we can send a message to a task to show its front panel what the normal program can't. So we can inject messages to debugging for debugging. So we can start them, we can hide them, we can stop them. Okay, this is an early concept from the task managers.
It's very interesting for unit testing, by the way.
Yep.
Does that work in the runtime environment?
Yes and no. If you don't have a front panel, it doesn't work. But if you remark or remember this when you build the application, then it works in the runtime engine too. So you can say every task that has a front panel, you can say to the VI, present your front panel. So if you have debugging in an output set there, so you can read what it's doing. So, but there's another part where we benefit from the object orientation of the system class. We have a system log implementation that's built in the system class. So every task can send debug messages. So there are some standard messages implemented in the API. So I'm starting a task, I'm killing a task, things like that. But it's possible to send individual messages for everything you are doing in your system. So if you then have an event that something is happening, you can see by the messages or the events that are listed in the syslog what's happening now. The event comes, this starts this and this action, this and these actions do that, and this is the conclusion. So for example, we are using this these days at a customer. Our customer is in the automotive and he wants to build a test stand in LabVIEW. It was his decision. He wanted to do a task system, what's the word? A dispatcher system for operational testing of its devices with LabVIEW. So there we need that. We are spawning tasks that dispatching functions, but the control of that is not in our LabVIEW program. It's made by the program the customer writes in his own, what's it called, test? Test bench, yeah. It's test bench, the name from the tool. It's producing XML-based test sequences, and these sequences are parsed in the program, and we are working these test cases each by the other in the dispatcher. And the dispatcher starts other dispatchers to make sub-processes. And all this interaction there is only debuggable with such a syslog system. But again, a big problem. Debugging interacts with the system, so with debugging on, you get different behavior with debugging off. Okay, you can discover the race conditions. You can, it's multi-client compatible. For example, if you use, on the one hand, a Windows UI, and on the other hand, you have a real-time target with a dispatcher or something like that on it. And these two interact via the task TCP/IP communication. So you can start a process on the UI by sending the message. The UI writes in the syslog, I'm starting this event. BRT quits that it has received the new order and says again what it's doing and sends the message back, and everything can be logged in the syslog to see what's happening. Okay. So, at this time, questions.
The last bullet, how do you filter? You can filter by task, or the last one is filter messages.
Yeah.
Can you explain a little bit about?
Yep. There is a function in the system class. I can show it in the demo if it works. To send a debug message. So these debug messages can be sent to several directions. First direction is it makes a local file copy of the most important events. So typical situation at a customer, an error message is presented. You come to the customer and he says, yes, there was an error message every 2 days. Yeah, and what's on the error message? I don't know, I just clicked it away. So the syslog first writes this event to a local file. So you get always a logging of failures. So that's one part. The other part is via network. This is exchanged via UDP. So you can go with your laptop, put it in the network, and all the clients connect, and you see the messages from all the clients to the debugging syslog task program.
Can you monitor all messages going around? So they all have to go through this manager, right? Or duplicate it to
monitoring everything is too much. It's too much traffic.
Right. So that's why I'm saying. So you can select those that you want to monitor in
Yep.
this moment.
Yep. The programmer or the designer of the task has to decide what he wants to monitor on the syslog. So there are some processes, for example, unknown messages that are always sent to the syslog. These are the yellow ones, for example. This is typical for unknown task, unknown message. No, it's another thing.
So can you, if one actor sends a message to another, you want to debug it at some point, right?
Hmm?
So how do you reroute or duplicate that message for you to be seeing that, peeking into it from outside, from whatever?
So you need a small VI that started with the message or where the message is received. So you need a VI that says send to syslog a warning or a debug message, order received or this order sent.
So you need extra code that you can enable or disable.
Yep.
Depending whether you want to monitor that particular message at this point or not. Okay.
Typically, we use the conditional disable structure for that. So there's a flag in the disable structure debugging TCP/IP communication, enable or disable, and then with the conditional disable, it's turned off and on if the syslog messages are sent or not. So, what's the time? Okay, a lot of time. I think we have any more time, or are we done?
10 minutes.
10 minutes, okay. Then we can first, some future things we have to thought about. We want to implement DQMH plugin. So in the next level of the task, we can use DQMH actors as clients in our API. We want to build more LabVIEW VI scripting tools and more templates and examples. Sure, integration of the LabVIEW create new dialog, and research a way to visualize the message chains and the task hierarchies. That's the big problem the actor framework has either. You don't know which actor is working with which message at which time. So all the messages flying around, it's hard to visualize what's happening there.
Well, they restricted the clients of the messages only to be either children, basically, or the parent, whoever created. But that's ridiculous because, I don't know, a shop assistant interacts with the customer. He serves the customer, right? But he reports to his manager. So what? He cannot talk to a customer directly? That's ridiculous. But that's built in, hard coded into the actor framework as
That's
it is
not
right now.
really true, though. I mean, it's not a limitation of the framework.
The-
You can pass cues.
There is peer-to-peer communication in actor framework as it is by default,
Peer to peer.
or to the same level.
Pass their cues to whoever they want.
You can implement it,
Nothing
yes.
preventing you from doing that. You can pass the cues and register them.
They
That's
pass
fine.
it only. You can send the message only up the hierarchy.
That's not true.
That's not true anymore, or it was never true. That's
It
how
was
I
never
understand.
true.
Capture it somewhere, you need to read it somewhere else. Like, wherever you want to capture it, you
Yeah.
just get the reference to the queue. And whoever else has the reference can use it,
Right.
whether that be a peer or somebody else that's not related or whatever.
It's recommended
Yeah.
to only go in a hierarchical manner because it's a lot easier to reason about the program
Yeah.
when
They
you do that.
recommend going up and down the trees, but you don't have to do that.
I do what's not.
But I just gave you a use case when it's not feasible. I mean, it's too limiting.
Okay, so this is the implementation of the task creating and destroying API. So you have a root task. Here we start this log, and then we have here a simple VI primitive that is only a while loop and a stop button. This one is names are way at this stage. The execution system is always on reentrant, so you can start this task several times, or this VI several times. So in this example, here, I have this VI here and here, and start it at the position, and there's a blue screen.
What here?
I'm sorry.
Computer there? Oh, blue screen.
Blue screen.
Question for you. In your task manager, can you see what state each of the
Yes, because the stage, the task manager bases on a simple VI, on a simple VI that holds a state. So every VI sends its state to this central database, and you can look what state is inside. But if a task is lost, the system can look with a VI reference if the state of the VI is ready or is dying, or is invalid, bad, or hidden, something like that. Everything is managed in the task manager. It's again a thing that's implemented with the system class on the top level. So it's inherent to all the subtasks. And this is the point where I like the object orientation, because I have only to implement it and at the top level, and all the other tasks know what to do. You can try it again. So any questions?
How do you handle state explosion problem? Do you support hierarchical state machines in there?
Yes, it works.
So do you store that structure somehow externally? Is it kind of hard-coded nested ifs, or how do you handle that?
Every task has its own concern on its own data and
I
behavior.
understand, but say you have an actor, right? And that actor by itself has a structure, has a behavior that is better to be described by hierarchical state machine. Otherwise, you will have too many states, right? Too many transitions. So you have to, to abstract the levels of behavior itself. So HSM, right? State charts, whatever.
Yep.
Hierarchical state machine. How do you implement that? Or you leave it for the user to implement?
It depends on the task. You can do with the task what you want if you only fulfill the outside behavior, the task behavior. So it needs to interact with the task manager, with a functional global variable inside, to log in and log off. And what the task is doing with subtasks, it's his own thing. He can use its own method for that.
Sure. The actor can, if its behavior too complicated, right? So it can spawn other actors, right, with simpler behavior. So, but you may still want to, if it's a model of some oven, whatever. So by itself, it is a single object, right? But with a slightly more complex, very complicated behavior, you may want still to implement that behavior within the same actor. That's my point. So then, regular FSM is no good because you have too many states, too many transitions, right?
Yep.
So how do you implement hierarchical state machines, say, as for such an app?
Depends.
All right.
The best question I can give at this moment.
I'm asking because in the same 2004, I made my own framework. Was called LabHSM. I don't know if you heard. So, which I stored that very structure with the transitions and hierarchical structure of the state themselves externally. So the template, the code itself, was very similar to each other for each actor, right? But they would all have kind of interpreting that I didn't use XML at that point, but it was basically, text script for the state machine part itself. In which state, when which event when message we receive, what should we do, and in which state we should end up. Because basically that's the repeated process in an actor, right? It receives a message, or it generates an event by itself, inside itself, right? Because something can happen. It has its own life, right? It doesn't have to come from other actors. An event can be a result of some action that the actor itself takes, right? So on that event, basically, every time we need to decide, depending on the state we are, what should we do and what should be the next state. So that whole information, if you think about it, is just that information. It doesn't have to be code of nested if statements. You can pull it out, basically, right? And then you have basically an interpret every time when you get that event that would look up in that structure and decide what to do next and which state should be next. So I was wondering how you implemented that when you needed.
We have a state machine queue in one system implemented. So a task can send several next steps to that stack. So each iteration is handled one stack, and if one stack decides you want to do several decisions or several actions,
atomic actions,
he puts these actions on the stack, and they are worked one at each other
into a queue base.
In a queue base, yes. It's an internal queue.
Right. So, but do you have it centralized in a sense? So, okay.
That's implemented in some VIs. I think in the data acquisition tasks it's implemented, but in the normal tasks it's not.
Because I found it logical to with basically every actor template with that ability. So whether you will use it or not, well, it's up to you. I mean, whether it will be whether your state structure is
Yeah.
very complicated or very simple, it
Yeah.
doesn't matter.
Yeah.
You have to handle it the same way, and then that gives more flexibility.
Yeah.
If the code stays the same, you just change this data that describes
Yeah.
the structure of
Yeah.
the tree of the state machine, of states in the state machine, and the corresponding transitions and actions.
It depends, I think. Okay, let me at the last point show this short demo. So we have hopefully these simple primitive tasks, only a loop. The second type is with data that are passed to the task at start. Here is a variant. So it gets a variant, and in this variant there is the time, the wait time for the loop. So, creating the task, starting the task, making the position of the front panel, opening the front panel, waiting 5 seconds, stopping it, destroying it. It's in all rows the same. These were the primitives. Here comes the two complex tasks. The normal panel, and hopefully it opens. Yep. So here we have the startup process, the registering of the events, panel on, front panel on, and the occurrence to the startup process, yes, I'm running. So now you have here a simple event-driven state machine. So here comes a message and the data, and depending on the message, it can do something. Here we have only the order show implemented. Order show turns off the panel, opens the front panel at some position, and turns the panel on. And here is this function for all the default reactions. If I open that, you see it's overwritten for data acquisition. And here in the primitive one, in the normal panel class, it handles several things. First of all, here, the default. Default is unknown. And in the unknown, here is the first reaction on the system log. In the syslog, you find, again, this function. So, the message written to the syslog is parameterized, and here you can say it's a warning, an error, it's a critical message, it's an alert, an emergency, etc. pp.
So you have priorities for messages,
We know that's for the syslog.
not just for the system.
It's just for the syslog.
So you don't have priority as an attribute
There
of
is
a message.
there is the priority that is available in the event messaging system. So you can prioritize messages to others, but I don't know how good it works. So it's possible to send a high priority message, but I don't know how good it works in LabVIEW. The message is implemented. So, and then for example, if you have an error message, the error message is taken from the variant and put in your local queue, in your local error cluster. So your error handler will react on that. Or here, the order halt. A notice is written in the syslog that I got the halt order, and then I sent back to the main queue, the main loop halt. So this is handling the default orders every panel can handle. So because of the time, I start everything together with syslog 2. There it is. This is the syslog monitor. I'll start it. bottom. And then I start this VI here. So, here is a subpanel where this, the next one, the subpanel, is showing itself inside. I start this one. Several things are starting here. The pop-up panel, the 4 types of created primitives, and everything is done after 5 seconds. Because after 5 seconds, everything should be killed. So, in the syslog, you see, started the application, subpanel start up, VI panel start up, and there you see the implementation of the syslog is only in the task classes and not in the primitives, because the primitives don't know anything about the message system. So, I hope you can see the subpanel here. Oh, you can't. There it is. So the subpanel itself works the same like a pop-up panel. It's, in general, the same VI. Yes?
So Actor Framework has a handle last act message. Is there that type of a feedback? Like you shut it down, can the caller get some final message saying that when it's shut down, when it is actually done? Because the child might have some shutdown to do,
Yep.
right, when you tell it to stop. So is that kind of built into it?
Yes, we build it in. So we have two possibilities for that. First, each task has to concern to its own child. So, if you shut down a task in the right way, so if you don't kill it out of the memory, if you use the normal stop-hold procedure, then it's going through the dinit subpanel. The dinit subpanel cleans up its references, and here it's shutting down its own childs.
So what's the mechanism of shutting down the child?
Sending a message.
Sending a message?
Sending a message to the child and wait if the child puts itself out of the task manager.
Don't you maintain a reference to whatever event structure in the parent for all children? Say if you used queues, right? You could if you have a reference to it, you could just kill the queue. That guarantees that
we need
the child
to finish over time. There's a lot of implemented. I'm sorry, but we have to hurry up. So thanks for listening. We can discuss this outside, and I can show you more demos if you want. Thanks.